propagate that gravity in a quadratic form. So 1, 1, close.
Okay. Okay, so let's start. So in the dualities we discussed in the past 2 lectures, which relate to the singlet sectors of free or critical vector models to higher spin theories, we often mentioned that one important feature was this projection to the singlet sector of the vector models. So there was this UN or ON singlet sector projection, which meant that we only wanted to look at operators which were UN or ON invariant. And we imposed that by hand, but there is actually a natural way to do this. Natural way to understand this projection, which I want to discuss today, which essentially what we can do is regard these symmetries, which are global symmetries in the vector models in the way I wrote them, but we could regard them as gauge symmetries by introducing a gauge field. So we can gauge the UN or ON symmetries and get then some kind of UN or ON gauge theory. And then we can, in that theory, it's natural that we should only look at gauge invariant operators, so UN or ON invariant operators. And to define the singlet sector of those vector models that I described yesterday, we take the zero gauge coupling limit. We take a limit in which we make the gauge interaction weaker and weaker. So the zero gauge coupling limit will give the free or critical vector models in their singlet sector. Okay, so this is a way in which you could phrase this projection. You just say that you make a gauge theory, and then if you want to describe the dynamics of singlet sector operators in this free theory, you can regard that as the zero gauge coupling limit of this more general gauge theory. Now this suggests then an interesting generalization of this story in which we don't have to keep this gauge coupling to 0. We can look more generally at the gauge vector models and just regard the dualities that I described so far as limits of zero gauge coupling. But we could study more generally non-zero gauge coupling. So in 3 dimensions, there is a very natural way to make this procedure, which is consistent with conformal invariance. So in D equal 3, we can do this by using Chern-Simons gauge theory. So for example, let me write it down in the case of the fermionic theory, but you could do similarly in the case of the scalar theory. So we can introduce the Chern-Simons action. Right, so let's consider the case of UN. So take UN Chern-Simons gauge theory at level k. Okay, this k is an integer in Chern-Simons gauge theory. A is a usual gauge field of UN with a trace here, and we couple that to our vector-like fermion field. So now this fermion is in the fundamental of UN. I can couple it naturally to this gauge field, right, in the usual way. Right? I'm omitting the I indices that I was writing yesterday, but of course these are vectors, so they're in the fundamental of UN, and this is a matrix, right, in the adjoint. Okay? So we have this more general gauge theory in which we couple the fermions to the Chern-Simons field. And since k here is like plays the role of the gauge coupling constant, more precisely k is the inverse of 1 over the gauge coupling constant square, the limit k going to infinity is an explicit way of saying this kind of limit. So in the limit k going to infinity, decouple A, and we get just the dynamics of this vector model built of fermions in the singlet sector. We still want to retain the condition that we only look at gauge invariant operators because we started from a gauge theory. Okay? Okay, but as I said, this now gives us the possibility of studying more generally this theory, not just this limit in which we decouple the gauge field, but we can look at this more general theory in which we don't send k to infinity necessarily. Okay? So in the large n limit, which is what I will be interested in mainly, so in large n limit, it's useful to introduce the 't Hooft coupling, as you are familiar with in gauge theories. So in this Chern-Simons theory, the 't Hooft coupling, the 't Hooft limit is defined as kn going to infinity with lambda n over k. So this is what plays the role of 't Hooft coupling here, fixed. Okay, so k is like 1 over g squared. So this is the analog of the 't Hooft coupling in the usual gauge theories, right? And this defines the 't Hooft limit in this Chern-Simons theory. So we can study this theory at large n, taking this 't Hooft limit, and we can do 1 over n expansion, and each coefficient of the 1 over n expansion will be a function of this lambda, right? Usual thing that you have in larger limit of gauge theories, right? So in this language, lambda going to 0 will be the free large n vector model in the singlet sector. Okay. As I said, you can do the same for scalar. You can couple the scalar to gauge field, but let me just stick with the fermion, and most of what I can say you can translate to the scalar. Okay. So first, let's discuss a little bit more about this model. So one first important so now we want to study what are the properties of this model, not at zero coupling, but at finite coupling. Let's say at finite lambda, still in the large n limit. So one first important property is that this model is still a CFT for any n and lambda, okay, or any n and k. Okay, so that's the first observation. So the way to see this, or the way to argue for this, is that this coupling constant here, this k, is quantized, so it cannot run. It doesn't have a non-zero beta function. So this is an exactly marginal coupling in these theories. And there are no other marginal couplings that we can generate. There is just one relevant operator, which is the mass term for the fermion, and we can tune that to 0. If we tune that to 0, we have a CFT for any n and lambda. Okay, so introducing this gauge field does not break the fact that we have a conformal field here. Okay, any question about this? It's because if you require that this action is invariant under large gauge transformation, then consistency requires that this is quantized. Now, people have checked this explicitly in perturbation theory. You can compute the beta function for this coupling constant, and you can verify that it's 0. I believe it's been checked up to 2 loops or 3 loops. I don't remember. Okay. All right. So this is one important property. So we have a family of CFTs. Parametrized by n and lambda, which are this Chern-Simons theory, parametrized by n and lambda, plus the fermions. Okay. Similarly, as I said, we can define a family of CFTs coupling the scalar field to the Chern-Simons. I'm not writing the action explicitly, it's the usual action. In this case, there is a complication that there is one marginal term that we can write down with scalars in 3 dimensions, which is a 5 to the 6 coupling. So I don't have time to go into the details, but what happens is that that coupling is exactly marginal in the large n limit. And if you go a little bit away from the strict large n limit, you can find that the beta function for that coupling can be solved and relates this coupling to lambda. So you have still a family parameterized just by n and lambda. So here there is the possibility of adding this coupling. It has a beta function, which is a function of lambda and lambda 6. If you impose this beta function to 0, you get a relation between lambda 6 and lambda. Okay? Sorry. Okay. We could also consider generalization of the Wilson-Fisher fixed points in the presence of these Chern-Simons. So we could also those double trace deformations. So we will have the Chern-Simons theory plus fermions plus G phi I square. So we can repeat what we discussed yesterday now in the presence of this. And then this will trigger a flow from a theory in the UV, which is now not a free theory, but it's this Chern-Simons plus scalar theory without this coupling. So here you have the Chern-Simons plus scalar, and you flow down in the IR to Chern-Simons, well, to, let's call it critical scalar coupled to Chern-Simons. So here you have a generalization of the Wilson-Fisher fixed points in which you have an extra parameter, well, 2 extra parameters, which are n and lambda. Okay, and you can do a similar thing for the fermions, right? Where now you have in the UV the critical psi plus Chern-Simons, and in the IR you have the psi plus Chern-Simons. Okay. Okay. So far we already noticed something interesting. If we introduce these gauge fields, we still get some interesting families of CFTs, of conformal field theories. And all these conformal field theories should have some ADS dual. So what are the ADS duals? Well, we know that this introducing these Chern-Simons, we are deforming the vector models that I was discussing yesterday by this extra parameter lambda. So the dual will be some deformation of the higher spin theories that I discussed yesterday, type A and type B, by this parameter lambda. Now, are these deformations, do they still give some higher spin theory, or they give something different? It could be that this deformation by lambda just completely break the higher spin symmetry in the bulk and makes something like gravity. But this actually does not happen for these models. So the next interesting feature of these models, just point 2, is that they still have a higher spin symmetry at large n. So at n going to infinity and finite lambda, not just lambda equals 0, there is higher spin symmetry. This observation then means that whatever this deformation is of the bulk dual higher spin theories, it should still be a higher spin theory at the classical level. Okay, now let's try to quickly argue why. I want to be a little bit quick because we eventually want to reach Vasiliev equations. So by this fact, I mean that in these theories there are higher spin operators, Js, and the dimension of these operators is the dimension of a conserved current plus order of 1 over n. There is no anomalous dimension to order n to the 0. Okay? In other words, these currents are conserved up to, well, they are conserved in the n going to infinity limit. Okay, so this is similar to what we discussed yesterday for the critical Wilson-Fisher fixed point. The higher spin currents were not exactly conserved there, but they were conserved at large n, so that the anomalous dimensions were only generated at some bleeding order. And how do we see this? So let me just sketch quickly the argument. Any questions so far? It's going too fast. This thing is particular to 3 dimensions because we have the Chern-Simons theory that we can use. Yes. Oh, thank you. Thanks. Yes, so phi is dimension 1/2 in 3 dimensions, so that's classically marginal coupling. Okay. All right. So how do we argue for this? Let's recall what is the spectrum. Well, let's try to understand what is the spectrum of operators in this theory, which is the spectrum of gauge invariant operators, single trace operators. Okay, so recall at lambda equal to 0, which was the free fermionic vector model, we knew that the spectrum was simple. We had a scalar operator and we had the higher spin currents. Right? Now what happens if we turn on lambda? Now we turn on lambda. We still have the same operators. Provided we covariantize these operators appropriately, right? We still have these operators. Make this covariant in the appropriate way. But these operators will still be primaries in our spectrum. And then the important fact is that there is actually nothing else. There is no extra operators beside this. And why is that? Well, the essential reason is that Chern-Simons theory is topological and does not provide any additional local operators. So the local operator spectrum does not get enlarged. Except for covariantizing these operators, we still have the same operator content. You could imagine that you could make some more general single trace operator by sticking inside those bilinears some powers of the field strength. Right? That would give a single trace operator if we put this inside those. But in fact, because of the special feature of the Chern-Simons action, the equation of motion fixes what this field strength is in terms of the fermion bilinear. So this is 1 over k psi bar j gamma rho psi I epsilon mu nu rho, which you can try to check. So what happens effectively is that if we stick any of this field strength inside those bilinears, we can use equations of motion. At the level of correlation functions, we can use equations of motion, and then that operator, which looks like a longer single trace operator, actually splits up into product of single trace operators. Because this, if we have here a bilinear psi bar I, here psi j, use the equation of motion, that splits into the product of two UN invariant operators, psi bar I psi I and psi bar j psi j. So we don't get any new single trace operators by using field strength. We will just get multi-trace stuff. So we only have these operators. Okay, we only have these operators with delta spin equal to 0 and delta spin equal s plus 1 s. This is the dimension in the free theory. Once we turn on the coupling, we expect this dimension to get corrected. Right? Now, so what happens to the currents? If we turn on the coupling, we expect that this current is not conserved, right? And here it should appear some operator with dimension s plus 2 in the free limit and spin s minus 1. So this is delta and this is the spin, because this operator here has spin s minus 1 and dimension s plus 2 to leading order, right? So if these currents get non-conserved, here there must appear some operator which has these quantum numbers, and this operator must be part of the spectrum of our theory, right? Now the only way that this operator can get anomalous dimension to leading order at large n is if this is a single trace operator. Okay? But there are no single trace operators with these quantum numbers, because we have enumerated all the single trace operators. Adding Chern-Simons does not add any new single trace operators. So there are no single trace operators like this. And so it follows that these currents have the dimension of a conserved current up to 1 over n. Okay? Now, in the same way that we saw yesterday for the critical Wilson-Fisher theory, this doesn't mean that this is 0 exactly. There are double trace operators which have the correct quantum numbers to appear here. It's just that there are no single trace ones. Okay? So okay, so what actually happens is that in the same way as we saw in the Wilson-Fisher theory, this right-hand side, this non-zero right-hand side here involves double trace operators. Okay, so there is, again, as I was writing yesterday, this is schematic. It just means that there is an operator here which has the right quantum number to match the quantum numbers on this side, and it's a product of two single trace operators. And here there is some function of lambda over root n, and there can also be, let's see, another function g over n and triple trace operator. Okay, so let me just write it like this. Okay, so this is what actually happens in these theories. The divergence of this current is equal to a combination of double trace and triple trace operators. Okay. So this is again same as what we saw yesterday, and then this implies that the actual dimension of these operators is s plus 1 plus some function gamma 1 of s and lambda over n plus order of 1 over n squared. Okay? So again, the important point is that there is no gamma 0 of s and lambda here. This is not present. Okay? So this is what Pedro would call f of lambda in an equal force superior Mills. In this theory is not there. It starts at 1 over n. Okay? Maybe I'm going a little fast on this, but let me give you two references in which you can read this in more detail. Well, okay, I don't have the archive number, but it's a paper by myself, Minwalla, et al. In 2011, and also Aroni, Gurari and Jacobi, also basically the same time as that. So here we concentrated on the fermion story, and here they concentrated on the scalar story. So you can read in more detail the arguments that I went over a little bit quickly now there. Okay, so but to summarize, the important point of this making this gauge theories is that 1, we still get CFTs, 2, we still get theories which have a higher spin symmetry at large n. Okay, so the anomalous dimensions are only generated to 1 over n, which means that in the dual theory, there will be a generation of anomalous dimensions through loop effects, but not at tree level. So the equation of motion of the dual theory will still be a higher spin theory. Okay, will still be some kind of Vasiliev theory, and we will see what it is. Okay. So this basically led to generalization of the Klebanov-Polyakov conjectures that this Chern-Simons couple to vector models, fermion or scalar, must be dual to some higher spin theory in ADS4, which will be a parity breaking theory because on the CFT side, the addition of the Chern-Simons term breaks parity. Okay, so this will be neither type A or B, which is what I mentioned yesterday, but some different theory. Okay, it's neither type A and B. It will be parametrized by some free parameter, which will get related to lambda here. Okay, and for lambda equal to 0, you'll get either the type A or type B theories, reproducing the dualities that we discussed yesterday. Okay. Any questions? Because by matching quantum numbers, you see that there is nothing else. You cannot go higher than triple trace. So on this side, you have an operator of twist. Let's call it twist delta minus the spin equal to 3. Okay. Double trace operator have twist greater or equal than 2, and triple trace operator have twist greater or equal than 3. Okay? And so if you go to quadruple trace, you already exceed the 3, so it cannot appear. Okay. All right. So let me close this part by just making one final comment. Just again to emphasize that there are two important features which are needed for all these nice properties to hold. One is that we have Chern-Simons. That gives us a conformal field theory for any value of the coupling, and it also makes the local operator spectrum remain basically the same as it was without Chern-Simons. It doesn't increase the number of local operators. And the second feature that is important is that we have vector models. That again is important because it makes spectrum of single trace objects just bilinears. Okay? If we consider this action in which, let's say, we have Chern-Simons plus an adjoint fermion, okay? Now, the part in which I said that we get a conformal field theory for any value of n and k is still okay. But in this theory, there is no higher spin symmetry at large n because of the fact that here now we have adjoint fields, and when we try to study non-conservation equations of this type in a theory with adjoint fields, we can have single trace operators appearing here. Okay? And then in those type of theories, you generate anomalous dimension for higher spin operators already at leading order large n. So already at 3 level, the dual theory is not a higher spin theory. Okay? The higher spin symmetry will be already lifted at leading order in this kind of models. Okay? Okay. Questions? Okay, so now we leave the CFT for a while, and we go to the bulk and try to describe equations of motion for higher spin fields in ADS. Okay, so first we want to briefly review the Frontal equations I mentioned in the first lecture. So these are off-shell gauge invariant equations of motion just for free higher spin fields. Okay. So we will start with flat space, and then we'll try to see what happens in curved space. So start with RD or D minus 1, 1. Now I'm using the letter big D for the space in which the higher spin fields live. I was using small d for CFTs. Eventually this big D will be small d plus 1. Now I'm just keeping it like this because I'm start with flat space first. Eventually we will go to ADS big D, which is ADS small d plus 1. Okay? So we basically want to generalize what we know for low spins, for low massless fields. So for S equal 1, we know that we have Maxwell equations. And there is the gauge invariance, right, with a scalar gauge parameter. And this, of course, can also be written in this way. Okay. For spin 2, we have Einstein. Now I'm just discussing free fields for now, so we want linearized Einstein. So the Einstein equations with zero cosmological constant, now I'm focusing on RD for now, are just this. And if we make the metric equal to flat plus fluctuations, right, then we get the linearized Einstein equations, which are right here, which I'm sure you all have seen at some point. Okay, those are the linearized Einstein equations. If you've never seen them, you can spend 10 minutes trying to derive them from the Einstein equations by linearizing it. Okay. Now we want to generalize this structure to higher spins. First, we want to understand the equation for free higher spins. So we want to generalize something like that. Okay. So we want some field with S indices. Okay, I didn't write here. Of course, there is the linearized gauge invariance here, which is mu plus mu, where epsilon mu is the vector parameter, which just descends from the general diffeomorphism invariance of the theory, right? So how do we generalize that to higher spins? So we want a structure like this, where this denotes symmetrizations over all indices, right? Now the story and the story with which Frontal actually reached this equation is a bit long, and I'm not going to derive the way he actually arrived at his equations. He started from some known equation for massive higher spin fields and tried to take a massless limit. In the end, he got equations. That's a little bit hard to do, so it's easier to just state the final answer and then check that the equations are gauge invariant. Okay, so let me state the final answer. The final answer is that to describe these fields of shell, we need this to be a double traceless field. Okay, so this is some off-shell constraint that you impose in your theory. Okay, it's not a gauge fixing. It's just that the equations of motion require, as we will see in a second, this constraint. And later, when we do a different formulation of this, this constraint will appear to be more natural. But for now, just state that our field is double traceless. Okay, so this is become non-trivial starting from spin 4 and up, obviously. Okay. Notice that this is, if we assume that there must be a gauge invariance of this kind, this constraint is gauge invariant, provided this parameter is traceless. Okay, so this is gauge invariant constraint if epsilon mu 2 mu s minus 1 is 0. Okay, so to proceed, we just postulate that we have a totally symmetric field which is double traceless. It's subject to this higher spin, to this linearized higher spin gauge symmetry, where this gauge parameter is symmetric and traceless. Okay. Now, given that these are the assumptions, you can just guess a structure of this kind. You can write down all possible terms which are up to 2 derivatives, because we just want to, in the end, get some usual propagation, 2 derivative propagation for the fields. You just make an ansatz and you check for which structure you get gauge invariance. I like this one more. Okay, so let me give you the final result. For the Frontal equation, it looks like this. Okay, so that's the result. Let's call this big thing here the Frontal operator, and we call it F. You can check that these equations are gauge invariant. If you do this gauge variation, you find, well, some coefficient here, which is not important, 3 derivatives acting on the trace of epsilon. Okay? You can put the indices here. It doesn't matter, okay? It's this gauge variation is 0, provided the gauge parameter is traceless. So the details of these are left as an exercise. Okay? And we can also write down gauge invariant Lagrangian. Or let's say action. It takes following form. Okay. That's the Lagrangian. You can check that this Lagrangian gives those equations of motion, and the Lagrangian is gauge invariant provided the gauge parameter is traceless and phi is double traceless. Okay? So at free level and in flat space, there is no problem. It's just a little bit cumbersome to work this out in detail, not too much. But you can write down consistent gauge invariant equations and consistent gauge invariant Lagrangian at free level. Okay. Now to see what are actually the propagating degrees of freedom, you have to gauge fix, right? And you have to check that this model describes correctly the polarizations that you expect for a massless field. Okay. So one convenient way to gauge fix to use the gauge symmetry to choose the field to be transverse and traceless. So this would be the analog of the Lorentz gauge that you get in spin 1, for example. There is an analog of that in this form. I'm not going to show you that you can do this, but it's not difficult to see. You can use the gauge symmetry to choose this gauge, and then the equation become very simple. If you choose this gauge, they just become Klein-Gordon equation for each of the components. Well, then, of course, we have those two conditions. Okay, but there is, as a familiar in the case of electrodynamics, when you choose this Lorentz gauge, there is a residual gauge symmetry, right? Which is gauge symmetry by epsilon. such that epsilon is minus 1 is harmonic and transverse. Okay, so then the counting of the propagating degrees of freedom is simple. You just count how many components a transverse traceless field of spin S has, and you subtract the components of this residual gauge symmetry. Okay. So let's call it GS minus GS minus 1, where this GS is the number of propagating components of a transverse field of spin S, transverse, totally symmetric and traceless. Okay. For example, in B equal 4, it's well known that these are just 2S plus 1. It's like the number of components of a spin S field in 3 dimensions, because you can go down to the little group, which is O3. Okay, and so you get the number of degrees of freedom is 2S plus 1 minus 2S minus 1 plus 1, which is 2, right, for any spin. So those are the two helicity, plus and minus S, that you expect a massless field of spin S to have in 4 dimensions. Okay, you can generalize this to higher dimensions. Let me write down here the formula, and you can have fun trying to derive this formula. Okay, this is in general dimensions. So, as it's well known, in dimension greater than 4, the number of propagating degrees of freedom of a massless field is not 2. It's more than 2, right? You can see from that formula what it is. Okay, so this was for flat space. Any questions? Did anybody ever see Frontal equation? Okay, now what happens in curved space? Can we put these equations in curved space? Okay. Of course, if you have those equations in flat space, the natural minimal thing to try is just to take those equations and covariantize them, right? Just send all derivatives to covariant derivatives. Can try the same equation, so call f m1 ms, but where we replace the derivatives by covariant derivatives, right? Does this give the correct Frontal equation on a general curved space? And of course, the gauge symmetry will be this. Does this work? Well, the answer is that it does not work. Okay. If you just do this, you don't get gauge invariant equations. Okay, it does not work. So the first people who studied this were Aragon and Deser in 79. Okay, what you can see is that starting from spin greater or equal than 3, in the case of, well, if you include half integer spins, actually the problem starts at 5/2. Okay, but in these lectures I'm focusing on integer spins. So starting from spin greater than 3, you find that this gauge variation always involves terms which include the full Riemann tensor. And for arbitrary, there are non-zero terms in the variation. this is non-zero, and this non-zero contains Riemann tensor. Not contains the full Riemann tensor. And because the Riemann tensor is in general unconstrained, if we got a Ricci tensor, then we could hope that maybe in some particular solution of Einstein gravity we could compensate the variation. But here we get the full Riemann tensor. So in arbitrary space, there is no way to make this procedure work. Now this sounds like a technical problem related to Riemann tensors and so on. But there is a physical reason why this doesn't work, because if it did work, then we could, if with this procedure we could get a Frontal equation in arbitrary curved space, we could then try to expand the metric in flat plus fluctuations, and from a term containing a spin S and 2 graviton, we would read off a consistent cubic coupling in flat space between these fields. But this kind of couplings are not allowed by the Weinberg low energy theorem. So this is consistent with what we expect, okay? So what's the way out? Because it cannot work on a general space, the only hope is that it works in some very special space, okay? And let's leave this board here. So resolution, well, not really a resolution, but it works on maximally symmetric space only. So if we choose the background in which our spin S field propagates to be maximally symmetric, so that the Riemann tensor is it's written like this. It's related to products of the metric. Okay, where this would be the radius of the maximally symmetric space. Right? The convention here is that if this is positive, this is ADS. If this L square is negative, it's de Sitter. Okay, so it's either ADS, DS, or of course flat, but we already know it works there. So in this case, it works. So we get this non-zero variation. When we do this gauge transformation, we get something which has the Riemann tensor. But because the Riemann tensor is so simple, you just get very simple terms, which can be compensated by just very slightly modifying this Frontal operator by adding some non-minimal modification to it, which looks as follows. So in ADS or DS, we can get to gauge invariant equations of motion if we do the following. We take the operator in flat space, which is defined on that board there. We replace all derivatives by covariant derivatives. Okay, by itself, this minimal coupling is not enough, but because this, so if you do this, you get some offending terms here, which are Riemann tensor, but those are very simple, and they can be compensated by just adding some mass-like terms of this kind. if you do this, then this is gauge invariant. Under the gauge variation by epsilon. Okay. So we will basically never need the full Frontal equations, even though it's good to know them if you actually want to check that Vasiliev equations reproduce at free level these equations. But for what we will actually need, we just need the gauge fixed version of these equations. So we can do gauge fixing in the same way as we did in flat space. So gauge fixed, the same gauge fixing, transverse and traceless phi. Then the gauge fixed equations in ADS or DS looks as follow. We basically just get the effect of this extra term that we needed to add in order to achieve gauge invariance of the equations. So this appears here. And transverse and traceless. Okay? So don't get confused about traceless and double traceless condition. Double traceless condition is really an off-shell constraint that we need to write down the equations, even off-shell. This is a gauge fixing condition, okay, that we can impose, and then the actual propagating field in this gauge is traceless. It's more than double traceless. Okay. All right. So we have this term here, which looks like a mass, which sometimes may confuse people because we are talking about massless fields, and here it looks like we have a mass. But this is not a mass. It's just the precise coupling to the curvature that we need in order to achieve gauge invariance. So this should be still, of course, thought as an equation for massless fields. This is not a mass. Okay? To convince you of that, we can look at the example of spin 1, which you should all know. Okay? So for spin 1, we know that there is no problem putting it in curved space, in any curved space, right? The Maxwell equations are just covariant derivative of f mu nu, right? You all agree that these are the gauge invariant equations in any manifold, and this can be written in this form, so it's nabla square a nu minus del mu d nu a mu equal to 0. Now we can commute these derivatives here and write this as del mu, and then we have to add the commutator. Right? Now I don't have more space here, so let me switch Blackboard and go here. So what is that commutator? Commutator, this is nothing but the Ricci tensor contracted with a mu, right? Using just the usual fact that commutator of covariant derivatives gives curvatures, right? And in the maximally symmetric space, this is equal to -1 over L square delta mu mu d minus 1 a mu. Right? That's That's the Ricci tensor of a maximally symmetric space, right? It's R mu nu equal minus 1 over L square G mu nu d minus 1. Okay. So then we have the Maxwell equation in curved space. How was I writing it? Del mu, mu, plus 1 over L square d minus 1 mu is equal to 0. And you can check that this equation is exactly this equation that I wrote here in the case of spin 1. If you look at what is that operator for spin 1, you replace all derivatives by covariant derivatives, and then you add these extra terms. You will only need the first one because there is no trace for spin 1, and this coefficient is nothing but this d minus 1 that I have here. Okay, so in particular in the transverse gauge, we just get del square plus 1 over L square d minus 1 on A mu is equal to 0, right? Which is the same equation here, okay? So you should definitely not think of this as a mass, okay? In spin 1, it's completely clear. That's the gauge invariant equation. We just to produce this kind of terms if we commute derivatives when we want to impose something like transverse constraint, and then we get some simple Klein-Gordon equation where there is a term which looks like a mass, but it's not. It just comes from Ricci tensor. Okay? So the definition of massless in curved space, it's really that just that the equations are gauge invariant. Okay? Any questions? Okay, so in the same way as you can do in flat space here, you realize that there is a residual gauge symmetry of the same type, and the counting of degrees of freedom in ADS or DS is the same as in flat space. These equations propagate 2 degrees of freedom in 4 dimensions as they should. Okay? So Frontal equation can be put in flat space, ADS, or de Sitter space. It cannot be put in general curved background, and for reasons that are physically well understood. Okay. Now the question is, how can we make this interacting? Is it possible to modify these equations to produce some non-zero right-hand side here, which will be something quadratic in phi plus cubic in phi, and so on? Some kind of nonlinear theory and some kind of nonlinear generalization of the gauge invariance, so this only has the linearized gauge invariance. So the problem is to find a nonlinear generalization of this gauge symmetry, something like in gravity we know how to make a nonlinear generalization of the linearized gauge symmetry, it's just diffeomorphism. Here we need to find something like that. And then we need to find an appropriate nonlinear extension of these equations. Okay, so that turns out to be a very, very difficult problem. And in practice, in this approach, using Frontal fields, it has not been possible to carry out to fully nonlinear level. People were able to find out 3-point interactions, which would be something like a quadratic term on this right-hand side in terms of these fields. But going to fully nonlinear level in this formalism, it seems very complicated. So Vasiliev formalism starts from something slightly different, which turns out to be more suitable in order to get a fully nonlinear theory. Okay? So the Frontal approach is sometimes called a metric-like approach to higher spin fields. If you see these kind of words, what it means is just that Frontal field is like a generalization of the metric field, right? The linearized graviton is a symmetric tensor of rank 2. The Frontal field is a symmetric tensor of rank S. Okay, so that's what metric-like means. Celia formulation starts with something slightly different, which at linearized level is equivalent to that, but it's more suitable to write down interactions. It's called frame-like, and you can also call it Wilbein-like if you want. So it starts from generalizing the gravity written in terms of Wilbeins instead of metrics. Okay, so you know that in gravity we can use the metric, or we can describe the gravitational field in terms of a Wilbein, right? Where you introduce some local Lorentz indices, which I will denote as A, B, C, D, and so on. And this will be the curved indices. Okay, that's our Wilbein. And you can reconstruct the metric from the Wilbein in the familiar way, right? So these indices in this flat local Lorentz are contracted with the flat Minkowski metric, right? That gives you the metric. Now, of course, there is a redundancy in this because you can do local Lorentz transformations on this Wilbein, and you will get the same metric, right? And that's, of course, expected because this object is a symmetric tensor which has d plus 1 over 2 components, but this is just a matrix which has d square components, right? So that's d plus 1 over 2 minus d minus 1 over 2, plus d minus 1 over 2, and these are just the number of gauge parameters that you have, which are the local Lorentz transformations, right, which are d minus 1 over 2. So in this approach, you need to introduce some gauge field for this local Lorentz symmetry, right? So introduce a gauge field, which is the spin connection, which is the local Lorentz gauge field, where this is antisymmetric, right? So it has a number of components d minus 1 over 2, which is the same number of gauge parameters that you have in the local Lorentz rotations, right? I assume that this is all familiar to most people, right? Okay. Okay, one nice thing about this formulation in terms of Wilbeins and spin connection is that we can often use the language of differential forms, which allows to make some, well, it's more powerful for several purposes. So we can regard this Wilbein and spin connection as one form. So when I write EA, this means a collection of 4 one-forms parameterized by A, which is EA mu dx mu, right? And we can have a one-form omega AB, which is omega AB mu dx mu. And this is the starting point for the Carton formulation of gravity, which I'm not going to review in detail here, but it starts with the so-called Carton structure equations, which are nice equations written just in language of differential forms. There is no metric needed. So the first structural equation says that this is the torsion, right? And the curvature which you can build from the spin connection is the Riemann curvature 2 form, right? This is a 2 form. And one can always go back to the metric formulation by imposing torsion to be 0 and then solving the torsion constraint. This allows to solve omega in terms of the Wilbein, so omega becomes an auxiliary object. And once you solve omega in terms of the Wilbein, you can then verify that this definition of the curvature is nothing but the usual Riemann tensor. After you solve this this is just the usual Riemann tensor, which you can build in terms of the usual metric. Okay. All right. So this is just a very, very quick review of Wilbein and spin connection in gravity. Any questions so far? Okay. So one natural thing to do, which will lead to a very natural generalization to higher spin, is the following. So because these are one forms, and we already know that omega is some gauge field, it's natural to ask whether we can combine them into a single one form, which is the gauge field of some Lie algebra. Okay. So can we combine E and B into a single object, which I will call W? Okay, so we have a total number of one forms, which is d minus 1 over 2, which are the omega, plus d, which are the E. So this is d plus 1 over 2. And so the total number of generators that we would need in a Lie algebra, which we could use to combine E and omega into a single object, is d plus 1 over 2, right? Just this number of generators plus this number of generators. But we already know that these are local Lorentz rotation generators, so we know what the algebra of this is supposed to be. And we know that this is supposed to transform as a vector, so we basically know what is the commutation relation of M with itself and of M with P. And then there are not many choices that for what we can write down for the commutation relation of P with P. So there are only 3 choices, which gives us a Lie algebra, a simple Lie algebra with this dimension. So this will be the usual Lorentz, right? Plus minus the other terms. And this is also fixed by just the fact that the p's must be rotated as vectors. And if we want commutator of PA and PB, the only choice is to write down here. Let me make sure I get the conventions right. Okay, my notes are disintegrating here. I over L square M AB, right? So whatever you have here must be proportional to MAB, and there is just some something with the dimension of radius squared that appears here. So this gives us 3 algebras. If 1 over L is 0, that's just a Poincaré algebra. If 1 over L, let's call it 1 over L square ADS, that's the ADS algebra. And if 1 over L is square, it's minus 1 over L square ds, let's call it, that's the ds algebra. Okay, so this, of course, these are the isometry groups associated to the maximally symmetric solution of Einstein gravity with 0 cosmological constant, negative cosmological constant, and positive cosmological constant. So this suggests that we could combine the Wilbine and spin connection into one form of either one of these algebras, depending on the sign of the cosmological constant in our theory. So this is familiar in the case of three-dimensional gravity. This is precisely the starting point of reformulating three-dimensional gravity as a Chern-Simons gauge theory of one of these 3 groups. In that case, d is equal to 3, depending on the sign of the cosmological constant. But at the level of combining, at least kinematically, of combining Wilbine and spin connection into some gauge field of some algebra, we can do this in any dimension. In higher dimension, things are not as nice as in 3 dimension because there is not a natural action that you can write down for this W. Okay, but this is still useful because, well, it's useful. It's a useful thing to do. For example, to write down what are the gauge transformations that you expect for these fields. You can basically use the language of Yang-Mills theory, write down gauge transformation, which are correct. Okay, so can I get Pedro like 5 minutes? For example, one thing that we can do that shows that combining E and omega into a single gauge field is not silly, we can try to compute the curvature of this field using the usual rules of Yang-Mills and see what is that curvature. What is that curvature? Well, that curvature just reproduces the torsion and the Riemann curvature that appear in the Carton structure equations. So if you do that, if you do this calculation and use the algebra and group terms according to the generators, you get this structure. Okay, so when this is infinity, you literally get just torsion and Riemann tensor. When we use the ADS algebra or DS algebra, here we get this extra term. And now we see a nice thing. So there is a nice interpretation of what a flat connection is using this formalism. So what in a gauge theory we would call a flat connection, which is something with 0 curvature, is nothing but a maximally symmetric space. If you impose that this curvature is 0, you get the torsion constraint equal to 0. And from this equation, so well, we get this, which allows to solve omega in terms of E. And the second equation, just to give us d omega AB plus omega AC wedge omega CB is equal to minus 1 over L square EA wedge EB. But this is just a condition If you translate this in metric language, this is just a condition that the Riemann tensor is the product of metric. So this is the same as saying that Riemann is equal to minus 1 over L square GG minus GG. Okay? It's just written in that language. So flat connections have a very natural interpretation, which is maximally symmetric space. And this is actually how the ADS solution will come out from Vasiliev equations. There will be one equation which says that the curvature of this is 0. And if, well, there is a simple solution in which you can set the curvature of this to be 0, and that solution is ADS. Okay? Now, the other nice thing that we can do with this formalism is that, as I mentioned earlier, it allows us to guess the correct and nonlinear gauge transformations just by following our nose and using the language of gauge theory. We have combined E and omega into a single gauge field, so we can postulate, as usual in gauge theory, a zero-form gauge parameter, which is a combination of something in the direction of P plus something in the direction of M. And then the gauge transformation is just the usual one. Okay, you just write this, follow your nose, and you split it in P and A. Then you get epsilon A, gives some kind of local translation, and epsilon AB is what you expect for the local Lorentz. Once at the end of the day you re-express everything in terms of metric, what this gauge transformation gives is just the diffeomorphism in terms of the metric. Okay, so this translating from E and omega back into G mu nu, it gives us the correct nonlinear gauge transformation for the metric. Okay, this essentially comes from the local translations. This you fix by eliminating omega, and you get back to the correct transformation. So starting from this is then the idea of Vasiliev is to enlarge this W field to include also the higher spin stuff here. So here we have a gauge field in the ADS case of the ADS algebra, SOD minus 1,2, which is nothing but the conformal algebra. And we know that from the CFT side, we know that in the vector models, the conformal algebra gets enlarged to the higher spin symmetry. The conformal algebra is a subgroup, is a closed subgroup of the higher spin symmetry. So the natural idea here is to enlarge this gauge field, which is a gauge field of the conformal algebra, to a gauge field of the higher spin algebra. So now this W will become a bigger gauge field with more, well, with an infinite set of generators, where the spin 2 part will be this, and then there will be all others. And once we were able to write down that, then the nonlinear gauge symmetry will be just this, where we would have to define precisely what this commutator is. But then it's natural to get some nonlinear gauge symmetry. And then it's also natural to write down some equations which are invariant under this, just by basically following usual rules of gauge theory. But I have to stop here for today, so we'll do that tomorrow. So tomorrow you'll finally see the Vasiliev equations in ADS4. Questions? Yeah.
Here, is this formalism useful even without going to higher spin theory? Is the way of formalism?
Just for doing gravity, you mean? Yeah, well, it's useful in some sense because Well, it's basically Carton formulation plus, well, there's an extra thing that we want to regard this as a single gauge field. I'm not sure if you'll learn much more about gravity itself by doing this, but you can reformulate things in this language. In 4 dimensions, actually, just in the special case of 4 dimension, there is even an action that you can write down which looks like Yang-Mills action, which is quadratic in the curvature. So it's quadratic in this curvature, which looks like higher derivative, but it's not. It's equivalent to Einstein gravity up to the Gauss-Bonnet term. So in 4 dimensions, there's this action called the McDowell-Mansouri action that you can write down using this language. This is not as nice as the 3-dimensional story, but at least in 4 dimension, you could write an action in this language. Roughly speaking, yes. Yes. No, not exactly, but almost. Any other question?